Well, data is all about decision making. Collecting data and not using it for decision making is by definition pointless. Every bit and byte of data we collect, we do with the view to making some sort of decision on the basis of it. So if we're only pulling 0.1% of that data, our ability to answer even basic questions is pretty limited. If I look into questions here, I can tell it's a dog, what species it is, what breed it's wearing a collar. I stand zero chance of answering any of those questions using the 0.1% on the left. And this is the premise today. We have a customer in the connected car space. Their vehicle has over 1,000 sensors. They have only a tiny amount of bandwidth, so they're just pulling 10. With no intelligence at all. They're saying, we can only get 1%, so we'll just pick that 10. So they're just selecting one very, very small area of the data. What we do with the Gallium technology is turn that on its head a little bit and saying, rather than collecting a subset of the data at very high accuracy, let's take a small accuracy hit, maybe 1 or 2%, so we guarantee 98 or 99% accuracy, but in exchange we can pull a far bigger overall percentage of the data set. So the image on the right here is a little bit blurry. We've sacrificed a little bit of accuracy, but I can still tell it's a dog, I can still tell what breed it is, I can still tell whether it's wearing a collar. Now, there are always people that say, oh, but there are questions you can't answer. Tell me what colour eyes does it have? And that's true. There will always be questions that we can't answer using this, and we don't advocate throwing away the rest of the data. We say absolutely store that, but just dip into that remaining volume of data when you have a very specific question to answer. So to give you an idea of what this looks like, so we operate exclusively in the time series data set. So this is, you can call it IoT data, time series data, telemetry, there's various terms, but they all basically mean the same thing. If you can graph it and you've got time on the x-axis, it's time series data. So if we look at what can you do with 100 to 1 data reduction, this is 1%. If I've only got access to 1% or I can only transport 1% of my data, what can I do with it? So I've been doing this in some way, shape or form for 20 years, and for 20 years there has been the same answer. If I have more time series data to process, store or transport than I have bandwidth available or capacity available, what do? I downsample it. That's the answer everybody uses all the time. Well, averaging or downsampling, we know what it looks like. If we look at the green data here as the original data, and the pink data is the average data, what happens? We lose all of the peaks and troughs and spikes, all of the interesting bits. And if this is vibration data, those spikes and peaks and troughs, those are very likely the ones that are actually telling me the most interesting thing. Those are very likely the ones that are the actionable information I need to jump in and do something with. So we've got accuracy here of probably less than 40%. So how many people want to make business critical decisions on an accuracy which is A, not guaranteed, and B, somewhere less than 50%? With the same data reduction, this is what we have with Gallium. Not super clear in this light, but there's an almost perfect overlay between the pink data and the green data, somewhere of order of 99%. And we've got this running live with an IoT example on our booth in the exhibition hall. If we look at that in context, this is a connected car use case. As I said, today we've got a customer who's taking 10 metrics out of 1,000. What would we do? We'd put Gallium at the edge. The edge can be in the aircraft, the edge can be in the car, the edge can be on the cow or on the fence post, the edge can be on the plant in the factory. And we might take 1% of the volume representing 99% of the accuracy, store the remaining on board. We may still additionally need to, or occasionally need to dip into it, bring that back, and that allows all of our analytics, our machine learning and our AI that we're able to do, but we're now able to do it on all of the sensors from the car at 99% accuracy, as opposed to 10 sensors at 100% accuracy. So we're getting a huge amount more business value for the same cost. Or, looked at another way, to the shoestring point, we could say, well, maybe we want 50 sensors, but we actually want to reduce our bandwidth bill by 2 or 3 or 4 times. So there's obviously a trade-off between how much you want to bring back and the cost. This is pure software, so we can deploy it anywhere. We can deploy it in brownfield sites. And we, as I say, we still store the remaining data locally for hookup. In the case of a car, it's when it comes in for service. In the case of an aircraft, it's when it goes in for maintenance or when it arrives at the gate. So I said there were 2 things that were holding all of these use cases back. The first one is that ability to transport data. Let's say you've solved that problem. The second problem is when you take this data from multiple sources, in a single place, it's volumetrically still very, very big. There's a huge amount of it. When we want to process analytics and we're doing it of thousands, tens of thousands, hundreds of thousands of devices, there's an enormous quantity of data. So I don't have the video here, we're playing this on our stand next door, but we take a very, very large data set and we process it twice. We process it at 100% accuracy, where a single analytical report, complex, but a single analytical report takes the best part of 2 hours. And we run the same analytical report at 99% accuracy, where it takes 9 seconds. So we've got analytical results for a user 700 times faster for less than 1% drop in accuracy. And if you look at it side by side, it's the same information. It's the same decision-making results. But why is that important? Well, the days of being able to make decisions on the output of a single report are gone. You know, if that was the only problem, you say, right, I'll schedule it at 6 a.m. It'll be in my inbox as a PDF when I get there. That's what we did in the late 90s, and we solved this problem just with brute force. The problem is that one-off report is very rarely enough to answer the question. The one-off report might give you a moment. What we want is the aha, where we do something actionable with it. And the journey from to aha is called data exploration. And so if we take that same 6.3 terabyte, 300 billion row, 4.5 trillion data point data set, what we're now doing in this recording is interacting with it in real time. Now, how many people can put their hands up and say, I can interact with a 6.3 terabyte, 4.5 trillion data point data set in real time? Zoom, filter, exclude, go into the data, realize it's a dead end, back out, go down a different path. So we go through 8 different exploration steps in 40 seconds. And this is a sort of frequency that users expect. If you're going to do data exploration and each mouse click takes a minute, users are going to give up and go somewhere else.